The rise of artificial intelligence has brought about a profound transformation across industries. This rapid evolution necessitates specialized methodologies to manage the complex life cycle of AI systems effectively. Without proper frameworks, the development and deployment of AI can become chaotic and inefficient. These methodologies are crucial for managing the entire life cycle of both traditional machine learning models and the increasingly powerful large language models. They provide structure and best practices for bringing AI from concept to production. This ensures that AI initiatives are not only innovative but also sustainable. At the heart of these practices are MLOps, or machine learning operations, and LLMOps, large language model operations. These are the key frameworks guiding modern AI development. They represent a critical shift in how organizations approach AI, moving beyond mere experimentation to robust, production-ready systems. These frameworks directly address the significant challenges inherent in building, deploying, and maintaining complex AI systems. From data management to continuous monitoring, they provide a roadmap for success. They help organizations navigate the intricacies of AI at scale. The core aims of both MLOps and LLMOps are multifaceted. First, they strive to streamline the entire AI development process, making it more agile and predictable. This reduces bottlenecks and accelerates time to market for AI-powered solutions. Second, these frameworks aim to significantly improve efficiency across all stages of the AI lifecycle. By automating repetitive tasks and standardizing workflows, they free up valuable human resources. This allows teams to focus on innovation and problem-solving. Finally, MLOps and LLMOps are instrumental in ensuring responsible AI development. They incorporate practices for fairness, transparency, and ethical considerations throughout the model's journey. This commitment helps build trust and mitigate potential risks associated with AI. MLOps focuses on automating and orchestrating the entire machine learning lifecycle. It bridges the gap between data science, software engineering, and operations. This integration ensures that models are not just developed but also reliably deployed and maintained. The ML lifecycle stages covered by MLOps are comprehensive. It begins with data preparation, which is foundational for any successful model. This stage involves gathering, cleaning, and transforming raw data into a usable format. Next is model training, where algorithms learn from the prepared data. MLOps ensures this process is repeatable and scalable. Following training, models are moved to deployment, making them accessible for real-world applications. Continuous monitoring is then essential to track model performance in production. This helps identify issues like data drift or concept drift. Finally, retraining mechanisms are put in place to update models with new data, ensuring their continued relevance and accuracy. MLOps principles are largely borrowed from the successful practices of DevOps. This includes fostering strong collaboration between data scientists, engineers, and operations teams. Effective communication and shared goals are paramount. Continuous integration, or C, is a core principle, ensuring that code changes are frequently merged and tested. This helps catch errors early and maintains a stable code base. Continuous delivery, or CD, then automates the release of models to production environments. Automation is a pervasive principle throughout MLOps. It applies to data pipelines, model training, testing, and deployment. This reduces manual effort and minimizes human error, leading to more reliable systems. Key components of MLOps begin with robust data management. This involves efficient data ingestion from various sources. It also includes thorough cleaning and transformation processes to ensure data quality. Data versioning is critical, allowing teams to track changes to datasets over time. This ensures reproducibility and helps in debugging model performance issues. Consistent data management underpins all subsequent stages. Model development benefits from experimentation management tools. These track different model architectures, hyperparameters, and training runs. This provides a clear audit trail of development efforts. Model versioning is equally important, allowing teams to manage different iterations of models. This ensures that specific model versions can be deployed or rolled back as needed. Comprehensive tracking of model metadata is also vital. Model training involves the automation of the entire training process. This includes setting up environments and executing training scripts. Hyperparameter tuning is often automated to find optimal model configurations. Resource allocation is managed efficiently, ensuring that training jobs have access to necessary computational power. This optimizes costs and accelerates training times. Scalable infrastructure is a key enabler here. Model deployment focuses on seamlessly moving trained models into production environments. This often involves containerization technologies like Docker. Containers package models and their dependencies for consistent execution. Orchestration tools such as Kubernetes manage these containers at scale. They handle deployment, scaling, and management of containerized applications. This ensures high availability and reliability for deployed models. Model monitoring is a continuous process of tracking model performance in real time. This includes metrics like accuracy, latency, and throughput. It provides immediate insights into how models are behaving. Identifying model drift, where the relationship between input data and target variable changes, is crucial. This signals that a model's performance may be degrading. Monitoring provides essential feedback for retraining, ensuring models remain effective over time. MLOps builds directly upon the foundational principles of MLOps. It extends these practices to address the unique characteristics and challenges of large language models. While sharing common ground, MLOps introduces specialized considerations. MLOps specifically addresses the nuances inherent in working with LLMs. These models present distinct operational complexities compared to traditional machine learning models. Their scale and emergent behaviors require tailored approaches. One unique challenge of LLMs is their significantly larger size. These models can have billions or even trillions of parameters. This scale impacts everything from storage to computational requirements. Consequently, LLMs demand higher computational resources for both training and inference. Managing these resources efficiently is a major focus of MLOps. Cost optimization becomes a critical concern. Data privacy concerns are amplified with LLMs, especially when fine-tuning with sensitive proprietary data. Ensuring data security and compliance is paramount. Bias detection and mitigation are also more complex due to the vastness of training data. Explainability in LLMs remains a significant challenge. Understanding why an LLM generates a particular output is often difficult. MLOps seeks to develop methods for better interpretability and transparency. Key focus areas of MLOps begin with prompt engineering. This involves designing effective prompts to elicit desired responses from an LLM. Crafting precise and clear instructions is an art and a science. Prompt engineering directly influences the quality and relevance of LLM outputs. It is a critical skill for maximizing the utility of these powerful models. Iterative refinement of prompts is a common practice. Fine-tuning and adaptation are central to customizing LLMs for specific tasks or domains. This involves further training a pre-trained LLM on a smaller, task-specific dataset. It allows models to specialize and perform better on targeted applications. This customization can significantly improve performance compared to using a generic LLM. It tailors the model's knowledge and style to specific organizational needs. Efficient fine-tuning strategies are a key part of MLOps. Model evaluation for LLMs involves assessing their performance across various dimensions. Metrics extend beyond traditional accuracy to include fluency, coherence, and relevance. Safety and ethical considerations are also rigorously evaluated. Responsible AI practices are deeply embedded within MLOps. This includes proactive measures for addressing bias in LLM outputs. Ensuring fairness across different demographic groups is a continuous effort. Promoting transparency in LLM behavior and decision-making is another vital aspect. MLOps aims to provide mechanisms for understanding and controlling these complex models. Ethical guidelines are integrated throughout the lifecycle. Cost optimization is a major consideration in MLOps. Managing the substantial computational costs associated with LLM training and inference is crucial. Strategies include efficient model serving and resource scheduling. This optimization ensures that LLM-powered applications are economically viable at scale. It balances performance with operational expenses. Efficient resource utilization is a continuous goal. The AI model lifecycle, managed effectively by both MLOps and MLOps, begins with planning and data acquisition. This initial phase involves clearly defining the problem that the AI model aims to solve. A well-defined problem statement guides the entire development process. Gathering and preparing the necessary data is also a critical part of this stage. This includes data collection, cleaning, labeling, and transformation. High-quality data is the foundation for high-performing models. The next stage is model development and training. Here, data scientists and engineers build various model architectures. They experiment with different algorithms and configurations to find the most suitable solution. Models are then trained on the prepared datasets, learning patterns and relationships. This iterative process involves hyperparameter tuning and optimization. Rigorous evaluation of these models follows, using appropriate metrics to assess their performance and generalization capabilities. Deployment and integration mark the transition of a model from development to production. This involves deploying the trained models into live environments where they can serve real-world applications. Seamless integration with existing software systems is essential. This stage ensures that the AI model can be accessed and utilized by end users or other applications. Robust deployment pipelines are critical for reliability. Scalability and security are also key considerations during integration. Finally, the lifecycle enters the monitoring and maintenance phase. This involves continuous performance monitoring of the deployed models. Tracking metrics like accuracy, latency, and resource utilization provides ongoing insights. Retraining models as needed is a crucial maintenance activity. This addresses issues like data drift or concept drift, ensuring models remain accurate and relevant. Proactive addressing of any performance degradation or operational issues is paramount for sustained value. Adopting MLOps and LLMOps offers significant benefits for organizations leveraging AI. These frameworks accelerate the development and deployment of AI solutions. They streamline workflows, reducing the time it takes to bring models to market. They also lead to a substantial improvement in model performance over time. Continuous monitoring and automated retraining ensure models remain accurate and effective. This iterative improvement drives better outcomes for businesses. Furthermore, these operations frameworks help reduce operational costs associated with AI. By automating tasks and optimizing resource utilization, they minimize manual effort and infrastructure expenses. This makes AI initiatives more economically viable. Crucially, MLOps and LLMOps ensure responsible AI practices are embedded throughout the life cycle. They provide mechanisms for addressing bias, promoting fairness, and enhancing transparency. This builds trust and mitigates ethical risks. Ultimately, the adoption of MLOps and LLMOps leads to more reliable, scalable, and impactful AI applications. They transform AI from experimental projects into robust, production-grade systems. These frameworks are indispensable for any organization serious about AI success.